In order to more easily evaluate this angular momentum of their body about the center of mass, we can define a quantity known as the moment of inertia. Moment of inertia is the rank 2 tensor such that when dotted with the angular velocity of a body fixed frame B in the inertial frame I with IG, you get the angular momentum about G. And after a bit of derivation, it can be shown that IG has the mathematical form of this expression for a collection of particles, and that again turns into a solid body integral when you're talking about a rigid body. U here is the unity dyadic. The unity dyadic is the unit element of the dyadic vector space, such that any element of the space of any vector of the Euclidean vector space dotted into the unity dyadic, you'll note that I'm using 2 underbars to represent the dyadic, gives you back the original element. So that's why how it's the unity element. Its representation with respect to any frame, with respect to I or any other frame, is always going to be the 3x3 identity matrix. So this is the 3x3 matrix of ones on the diagonal and zeros off diagonal, like so. This is, of course, inner product. This is outer product. If you scan through this dimensionally, you will see that this produces, if you put this all into linear algebraic operations, will produce a 3x3 matrix, and that matrix is known as the moment of inertia matrix. The diagonal elements of the matrix are called the moments of inertia. The off-diagonal elements of this are called the products of inertia. The moments of inertia are strictly positive values in this formulation. The off-diagonal elements have to be symmetric, right? This is a symmetric matrix. And again, has this form for either a collection of particles or for an extended rigid body. And if you have a density function, you can turn the integral into a volumetric integral instead of a mass integral. We can also think about what happens if we want to evaluate things with respect to an arbitrary point in the body that isn't the center of mass. And for that, we apply what are known as the moment transport theorem and the parallel axis theorem. So moment transport tells me that for an arbitrary point Q in the body, the moment about Q will be the moment about G minus the position of Q relative to G crossed with the sum of all of my external forces. I can apply Newton Euler-second law about point Q just as easily as I can apply it about point O or about point G, but I just need to do a little bit of a modification. If I take the vector derivative in the inertial frame, using the transport equation, change this to a body frame derivative plus the angular velocity crossed with the angular momentum, then I will get the moment about Q plus the position of Q with respect to G crossed with the total mass of the body times the inertial acceleration of Q with respect to point O. And so if Q is not accelerating in inertial space, if, for example, I'm talking about a fixed point in space, like, for example, in the case of a compound pendulum, this is very common, I might have my point Q being the attachment point, then this will go to 0 because the fixed point Q is not accelerating in space. I can evaluate H sub Q, again, just the same way that I defined H sub G by finding the moment of inertia about Q and then dotting it into the angular velocity of B and I. And to get this, assuming I already have my moment of inertia about G, I can apply the parallel axis theorem. And so this tells me that I about Q is going to be the same thing as I about G plus this correction term that is a function of the offset between Q and G and the total mass of the body. Switching gears a little bit, in addition to the Newtonian dynamics that we get straight from Newton's second law, there's some incredibly powerful tools that we can develop by also thinking about work and energy. As a reminder, a force, call it F sub P, does work, which we'll call W, on a particle P when it displaces the particle along the trajectory, and we'll call the trajectory gamma sub P. And so formally, the work, which is a scalar quantity, on particle P due to the force F sub P is a function of the position and the trajectory taken, and is going to be equal to the path integral over the trajectory of the force dotted into the displacement, the differential of R P rho O. The kinetic energy of a particle is going to be defined as half the mass of the particle times the norm squared of the velocity. So the velocity vector dotted into itself. Again, this is a scalar quantity, but it has to be generated as a function of the inertial velocity. So you still can't get away from being careful about inertial frames and what frame you differentiate with respect to get your velocity, even when you're using energy methods. The change in kinetic energy between times t2 and t1 is going to be equal to the total work done on the particle during that time. However, work done by conservative forces, of which gravity is one, depends only on the endpoints of the trajectory. And that means that a closed path integral for a conservative force will be zero. The work done by conservative forces across a closed path trajectory is zero. Conservative forces, and only conservative forces, can always be expressed as the gradient of a scalar potential, which we will call U, which is analogous to our understanding of potential energy. And so a conservative force acting on particle P can be written as negative the gradient of some function U P rho O associated with this force, which means that the change in this potential from a time t2 to t1 is given by negative the work done by that force. And so the total energy of a system is the sum of the kinetic and the potential energy of the system. The total work is going to be the work done by all of the conservative forces, which is negative the change in potential energy, and all of the work done by non-conservative forces, which is the change in the total energy. And the conservation of energy law tells us that if we have no non-conservative forces, then we will have total constant energy, which means that in a system that is only affected by gravitational forces, and this describes a lot of the astrodynamic systems that we're going to be talking about, at least initially, then we should expect complete conservation of total energy. If there's non-conservative forces, then the change in energy is going to be the non-conservative work.